Okay, in this video we're going to be talking about solving trig equations. So these are going to look something like sine x equals 1/2. This is a very simple trig equation, and the point of illustrating this is to show you where the variable is going to be. So we're going to call it x, sometimes it'll be called theta, really could be called anything. It's the angle that you're looking for, and we're told that the sine of the angle is 1/2. And so our job is to figure out the angles that have a sine of 1/2. If it's a non-calculator question, that ratio 1/2 is going to be something recognizable from one of your special triangles, like a 30-60-90 or a 45-45-90. So the side lengths will be like a 1, a 2, a root 2, maybe a root 3, to be from one of those triangles. I tend to use the either unit circle or like triangles on the coordinate plane as a way to visualize this. So I'm going to sketch the coordinate plane, and I'm looking for quadrants where sine is positive, because here the answer is 1/2, that's positive. And sine is a y value, which are positive in the first quadrant and the second quadrant. So I'm going to end up with two solutions to this. I'm going to label x, which is the angle in here. It's a central angle. And I'm going to label the opposite and hypotenuse sides, because that's the information I have. That's what sine is. And now all I have to do is look to this and try to remember which special triangle it is. So it's a 1 and a 2, which are part of a 30-60-90 triangle. And across from the 1 in a 30-60-90 triangle, we always have the 30-degree angle. So this x is in fact 30 degrees. Sometimes these questions will ask for answers in degrees. If it asks for it in radians, we have to remember that 30 degrees is pi over 6 radians. But there's a second answer. X could also be this angle. Now the referenced angle is still going to be 30 degrees, right? Because it's the same triangle, it's just in a different quadrant. But the angle, the way I have to report it, is a 30-degree angle in quadrant 2, which would be 150 degrees. Or if I'm putting that into radians, it's a full pi minus 30 degrees, or a full pi minus pi over 6, which would be 5 pi over 6. So there are two solutions to this equation, two values for x in the first rotation around the unit circle. So I should have mentioned that x is going to be between 0 and 2 pi. Usually it will have some sort of interval like this with the question, so that you know how many solutions you're supposed to give. Because I could keep spinning around this circle and give another answer and another answer and another answer, because I could end up back in quadrant 1 and back in quadrant 2 and then spin around again. So there's actually an infinite number of solutions unless they tell you the interval that you're supposed to be looking at. If you're imagining it as a wave, a sine wave, the sine wave is also infinite, goes on forever. So it's going to give you some interval to look between, so that you're only giving solutions on that interval. And it's usually 0 to 2 pi, but they could change that on you. So we'll see if we can encounter some examples like that. All right, here's an example where it might be necessary to manipulate your equation first before solving it. So we're not going to be able to solve an equation that has cosine and sine in it, typically. I guess you can if the equation is laid out in a specific kind of way. Here we wouldn't be able to solve cosine 2x plus sine x equals 0 unless we do part A first, which says to write the expression cosine 2x plus sine x in terms of sine only. And so this is where I'm going to look to my identities in the formula booklet and see if there's a way I can write cosine 2x, but with sine only. And so indeed, I see in the formula booklet that cosine 2x is equivalent to 1 minus 2 sine squared x. So I'm going to swap out cosine 2x with this expression, and then I have this plus sine x at the end. Part B now says, so set that equal to 0 and solve. That's a pretty complicated equation, a lot more complicated than the introductory one that just said sine x equals 1/2. So here I have what's called a disguised quadratic. I'm going to put it in order, in its normal quadratic order, which is to have the term that is squared first, and then the term with x in it that isn't squared, and then the constant term. And if you'd like to imagine, you could use u substitution here. That might make it easier for you to factor. You can imagine that this is or y substitution. Really, you could substitute sine x with just a variable, and you'll see that it's like a quadratic type trig equation. So I'm going to try to factor this thing. I'll factor it with u, and then I'll switch it back to being sine after I've factored it. So I know that I need the first term to come out to negative 2u squared. So that could either be a negative 2u over here times a positive u over there, or that sign, that negative sign, could be on the positive u. and the 2u could be positive. So I have an option here. I'm going to try it, and then if I need to switch the signs, I will. Then I look to the 1 that's at the end, and I see if I can find something that multiplies to make positive 1. There aren't that many things that multiply to make positive 1. It's either positive 1 plus and a positive 1 or a negative 1 and a negative 1. So I'm just going to try this. So I look to what I have, and I imagine distributing this back together in my head. And I see that the first term works out and the last term works out, but the middle term would combine to give us a minus u based on the way the signs are now. And since I want it to be a positive u, I'm going to try switching these signs. I'm going to make this one plus and this one minus. And then indeed, all of the terms work out. So this must be the correctly factored version. So if I now go ahead and put sign back in place of u, I can see that the first parentheses is 2 sine x plus 1. And the second parentheses is negative sine x plus 1. And it equals 0. So when we factor, it must say equals 0. I should have established that at the beginning, but it did say equals 0 before I started factoring. And now I'm going to set each of these factors equal to 0. And now I have two pretty simple trig equations to solve that are more like the example that we had on the first slide. But we had to go through all the other algebra manipulations to get here. So in this equation, when I isolate, it's going to say sine x equals negative 1/2. And in this equation, when I isolate, it's going to say sine x equals 1. In both of these cases, if it was a calculator, I could just use inverse sine to get rid of sine. But if it's a non-calculator question, which this one would be, you have to go to your coordinate plane and see if you can figure out the angles on your own. So we're going to draw the coordinate plane, and we're going to imagine where the sine could be negative 1/2, which would be in these two quadrants. Sine is opposite over hypotenuse, and the angles are in here. So I'm looking to these triangles, and I'm thinking, what is that value for x? It's across from a 1 again in a 30, 60, 90 triangle. That's going to be the 30. So I know I'm dealing with the angle pi over 6. I'm giving my answer in radians because it says in the original question on the interval 0 to 2 pi, which means that they want their answer in terms of pi as well, so a radian measure for angles. And we're supposed to give all answers between 0 and 2 pi, which would be one full rotation around the coordinate plane. So x is going to be a pi over 6 angle in quadrant, let's see, quadrant 3. That would be 7 pi over 6. And it's going to be a pi over 6 angle in quadrant 4, so 11 pi over 6. Both of these are solutions. There are also solutions that come from the second equation, sine x equals 1. Well, that, when it says sine x equals 1, that makes me think it's quadrantal. It's going to be right on one of the quadrant lines or the axis lines. So I sketch a little circle and I try to figure out at which of these four corners is the sine going to be 1. And sine is a y value. So I know the coordinate at that point would be 0, 1, where the y value is 1. And so that's the only place where the sine could be 1. The angle there is 90 degrees, which in radians is pi over 2. All right, so there's a more complicated trig equation. And then we'll do one more, maybe where they change the interval on us. Let me look for a good one. Yeah, that's probably a good one. Okay, we'll do this example. So here they've changed the interval on us. They're only looking for solutions between 0 and pi. They could shorten the interval, as they've done here, or they could expand the interval. They could have said between 0 and 3 pi or 6 pi or something. So in either case, we need to think about our final solutions when we give them. The equation here is cosine 3x equals 1/2. And the way it stands now, I'm not going to be able to get rid of that 3 that's in there. There's no way to do that the way it stands now. What I can do is figure out what the angle is supposed to be, so what this 3x is supposed to be, using my unit circle, my coordinate plane, and then I can set 3x equal to that angle that I know it's supposed to be. So let's just do it. You'll see what I mean. We have a coordinate plane, and I'm looking for places where the cosine is positive. Cosine is an x value. That's positive over here and over here. And cosine is adjacent over the hypotenuse. So I can label these sides 1, the hypotenuse is 2, right? And the angle is the one in the center there by the origin. So it's, again, a 30, 60, 90 triangle because it's got those recognizable lengths. But now I'm looking at the angle that is adjacent to the 1, which would mean it's opposite of root 3. So the angle that is opposite of root 3 is going to be a 60-degree angle. So I have a 60-degree angle in quadrant 1 and a 60-degree angle in quadrant 4. And I'm not prepared to look to the interval yet. I'm only going to look to that when I'm giving my final solutions for x. Because right now what I've determined is that the angles that go here are pi over 3, which is a 60-degree angle in quadrant 1, right? Or 60-degree angle in quadrant 4, which would be, got to do a little mental math, 5 pi over 3. Okay, because 6 pi over 3 would be a full circle, that's 2 pi. So 5 pi over 3. So that angle inside of this cosine is either pi over 3 or 5 pi over 3. Or if I was to continue going around the circle again and again and again, it could be even, let's add 2 pi to each of these, right? So if I added 2 pi to pi over 3, I would get 7 pi over 3. That's as if I've gone around the full circle and then gone 60 degrees into the first quadrant. And 5 pi over 3, if I added 2 pi to that, would be 11 pi over 3. And this list goes on and on and on. And I'm going to put a whole bunch of those at the beginning because I am going to have to divide by 3 in the next step, right? Because what I now see is that 3x must equal pi over 3, or 3x equals 5 pi over 3, or 3x equals 7 pi over 3, or 3x equals 11 pi over 3, and so on. And this list can just go on and on, right? Because I can keep spinning around the unit circle and adding 2 pi to these angles. So I'm just going to put the first 4 and see if I need more, I'll go back and try to get some more. If I need fewer, then I'll just cross out the ones that aren't part of the final interval. So now I'm solving for x. Now I need to consider the interval that's given, which is between 0 and pi. This is what it told me for x, that I should give all answers for x between 0 and pi. So I'm going to solve for x. I can get rid of the 3 by multiplication by a third. So x is going to equal pi over 9. That is between 0 and pi, so that's one of the solutions. This one, when I multiply it by a third, will equal 5 pi over 9. That's within the interval, so I put a box around that. This one, when I multiply it by 1/3, is 7 pi over 9. That's one of the solutions on the interval. Put a box around that. This one, when I multiply it, is 11 pi over 9. Oh, that's bigger than the interval that we're asked for x, and so I don't need to worry about it, nor would I need to worry about any of the other solutions that come after that. So the first 3 here are going to be the solutions for x on the given interval. All right, and that should give you enough of a reminder so that you can solve some more of these for homework. That's all.